It's my pleasure to introduce John Griffin from the University of Washington, Seattle. And he's going to talk about order set partitions, Tanisaki, ideals, and varieties.
Thank you, Laura. At a high level, this talk is about certain families of rings, quotient rings of the polynomial ring, which have connections to different areas. So in particular, combinatorics in terms of their dimension formulas, in terms of representation theory, because they'll all have symmetric group actions, and we'll study them as SN modules. And geometry, they'll all be co-homology rings or coordinate rings. So here's a table summary of where we're going. I'll introduce two families of rings, Rnk and R lambda, that have been previously studied. And what I'd like to tell you is a common generalization of these two families. So first, Rnk, the generalized coinvariant rings of Haglund, Rhoades, and Shimozono. So here's some standard notation. Bold xn is a set of n commuting variables, and E sub d is the dth elementary symmetric polynomial. And Josh talked about the coinvariant ring of type A, which is the following quotient of the polynomial ring by all of the elementary symmetric polynomials. And we'll denote that by Rn. And it has several connections to these three areas. In particular, its dimension is n factorial. It has some nice bases indexed by permutations like the Schubert polynomials. Representation theory, because it has an Sn action permuting the variables. And it's isomorphic to the regular representation as an Sn module. And geometry, because it's isomorphic to the co-homology ring of the complete flag variety. And there's one more geometric connection, which I'd like to point out, which is that Rn is also isomorphic to the coordinate ring of the scheme of diagonal nilpotent matrices. That'll come up at the end of the talk. Maybe a little bit less well known though. So Haglund, Rhoades, and Shimozono generalized this by taking two parameters, k less than equal to n, and they defined the following ideal, Ink, where they take the top k degree elementary symmetric polynomials and also the kth variable powers. And they define Rnk to be the corresponding quotient ring. So in the case when n equals k, all of these variable powers turn out to be redundant in that case. And the ideal is just generated by the elementary symmetric polynomials. So it specializes to the covariant ring. And Haglund, Rhoades, and Shimozono generalized many of the known results to the setting. In particular, they have a nice symmetric group modular structure in terms of an action on ordered set partitions. So let OPNK be ordered set partitions into K blocks. And Sn acts on that set just by permuting the letters 1 through n. So here I've given an example with 3 letters and 2 blocks. And they were able to prove that this ring, as an ungraded module, is isomorphic to the formal linear span of those objects. And their motivation for defining this ring came from the delta conjecture. So first, let's recall that the Furbinius characteristic of a symmetric group module V, this is the symmetric function you get by summing over all Schur functions. So S lambda is the Schur function. Where the coefficient is the multiplicity of the irreducible spect module, and indexed by that partition. So it's a sum over all partitions of n. And if you have a graded symmetric group module with graded parts VI, the graded Frobenius characteristic is the Q series you get by writing down the Q polynomial where the coefficients are the Frobenius characteristics of the graded components. And now the delta conjecture of Haglund, Remmel, and Wilson gives a combinatorial formula for a certain symmetric function. So this is the result you get by applying a Macdonald eigenoperator to the symmetric function En. And implicitly, this involves two parameters, Q and T. And essentially what Haglund, Rhoades, and Shimozono were able to prove is that this ring Rnk gives a representation theoretic interpretation for this symmetric function. And so more precisely, they proved that the graded Frobenius is equal to this symmetric function after you set t equals 0 and you apply a minor twist. So rev q is the operation that takes a polynomial in q and reverses the coefficient sequence. And omega is the involution on symmetric functions that takes en to hn. And last year at FIPSAC, Brendan Pawlowski presented his joint work with Brendan Rhoades, where they proved that Rnk also has, it can be realized as a cohomology ring. It's the cohomology ring of the variety of spanning line arrangements. So they were able to prove that Rnk is isomorphic to this cohomology ring as graded rings and also as symmetric group modules. There's a symmetric group action on these lines just by permuting the lines. So that's Rnk. And the next family is R lambda, the cohomology ring of a Springer fiber. So first, the complete flag variety is the set of all complete flags. So a complete flag is a sequence of nested subspaces of C to the n, where the dimension of the ith subspace is equal to I. So as you go along this flag, the dimension goes up by 1 each time. And the Springer fiber associated to a partition lambda is the set of all complete flags that are invariant under acting by this a nilpotent operator, a nilpotent matrix of Jordan type lambda. And even though the symmetric group doesn't act on the variety itself, like in the spanning line arrangements case, it does act on the cohomology ring. This was, Springer was able to prove this. And it has some nice combinatorial connections because the symmetric group module structure coincides with what's frequently called M lambda. This is the Q span of all tabloids of shape lambda. Or if you like, in terms of ordered set partitions, this is the set of ordered set partitions where the size of bi is equal to lambda I for all I. And moreover, the top degree cohomology is isomorphic to an irreducible, the spect module indexed by lambda. So in this way, the Springer fibers give a geometric way of constructing the irreducibles, and it's inspired an entire new field called geometric representation theory. But how would you actually work with one of these cohomology rings? It turns out that this cohomology has a nice explicit presentation as a quotient ring. So De Concini and Procesi, and later Tanisaki, found explicit presentations. So in this talk, I'll follow Tanisaki's presentation. So Tanisaki defined the ideal I sub lambda to be a certain ideal generated by elementary symmetric polynomials in subsets of the variables. So remember, bold xn is the set of variables x1 through xn. And the generators you take are the ones that satisfy a certain inequality on the size of the subset. So P here is a statistic just summing up the last few parts of the partition. And it's not so important for this talk what that ideal actually is, but know that you can write it down, you can put it in a computer and start computing things. And R lambda is just the corresponding quotient ring. So De Concini and Procesi and Tanisaki were able to prove that this Co-Homology ring is isomorphic to this explicit presentation. And why do algebraic combinatorialists care about this ring? It turns out that its graded Furbinius characteristic has this very beautiful formula. It's just equal to the modified Hall-Littlewood function that Olio talked about. So recall that the modified Hall-Littlewood H lambda tilde is the specialization of the modified McDonald function that showed up in Olio's talk when you set t equals to 0 up to conjugating lambda. So those are the two families that have been previously studied, and they have nice symmetric group structures, and they're isomorphic to co-homology rings. So next I'd like to introduce a new family of rings which form a common generalization of these two, which I call R and lambda. So just as before, we'll take k less than or equal to n, and now, but this time we'll take a partition of the smaller integer k. Okay, I think my internet's getting a little bit slower, so my writing is going to get worse. And we defined the ideal I sub nk basically the same as the Tanisaki ideal, except since our partition is smaller, this p statistic is also smaller, and the effect is that we take high degree elementary symmetric polynomials. So we're modding out by fewer generators than before, and we'll let R sub n lambda be the corresponding quotient ring. Now, in general, this ring is an infinite dimensional vector space. Because we're modding out by fewer relations. So in order to correct for that and to be able to apply techniques for finite dimensional rings, let's also introduce another parameter, s, which is less than or greater than or equal to the length of the partition. And R and lambda s will be the corresponding quotient ring where we mod out by all of the s variable powers as well. And so just as a reality check, if n equals, when n equals k, then R n lambda s specializes to R lambda for any s. And then when lambda is 1 to the k and s equals k, we recover Rnk. So these really do form a common generalization. And these new rings also have a nice symmetric group module structure. So we'll let OP n lambda s be a certain subcollection of ordered set partitions where we fix the length to be s, and we condition that the size of the ith block has to be at least as large as lambda I. So for example, when lambda is 2, 1, and s equals 2, then we're looking at 2 blocks, and we're saying that the first block has to be size at least 2, and the second block has to be size at least 1. So in general, I'm allowing bi to be empty. So what I'm trying to write is that bi equals empty is allowed when I is greater than the length of lambda. Sorry, for some reason I'm not able to write right now. Okay, And Rn lambda s is isomorphic to the formal linear span of these objects. And in order to get a formula for Rn lambda, all you have to do is take a limit as s goes off to infinity. So that corresponds to allowing infinitely many parts. It's just that finitely many of those blocks will be non-empty. Now, to get a more refined statement, let's go to the graded Frobenius characteristic. So the graded Frobenius of Rn lambda s. So first, I'll define this in an example. So if lambda is 3, 2, I'll draw the conjugate partition in French notation. So this has columns of 3 and 2. And if S is 3, I'm allowing 3 columns. So I have a blank third column. And there's an index between ordered set partitions and labelings of this diagram where you take your ordered set partition and you use the elements of the first block to label your first column, except that some of these labels might spill out underneath, but that's okay. For all of these labels that spill out, we'll give them their own cell. So we'll call those basement cells. And an extended column increasing labeling is we do the same thing, but we allow repeated labels in a column as long as it weakly increases down each column. So here I have multiple 2s, but that's okay because it weakly increases down the column. And we define an inversion statistic on these labeled objects. So given B greater than A, 2 labels, they form an inversion if, so B is in the partition shape and A is either immediately to the right of it or in the next row and below it, and in the next row and to the left. So you might recognize this as the attacking pair condition if you've read Haglund, Heyman lore. Or if B is in the first row, we'll allow A to be a basement cell to the left of B. So in this example, we have three of those inversions. So the 2 is inverted with the 1. Let's see if I can mark this. And the 9 is inverted with the 2 basement cells labeled 7. So in this example is first you write down 3. And in order to get the right count, we'll also tack on for each basement cell in column I, we'll count that as I minus 1. So for example, this 10 counts for 1 because it's in the second column. And the 4 and the 5 each count for 2. So in this example, the total number of inversions is 3 plus 5, which is 8. And I should, so this inversion statistic is really just a variation on a co-inversion statistic introduced by Rhoades, Yu, and Zhao. They proved a Hilbert series formula for these rings. And it turns out that that Hilbert series formula extends to a graded Frobenius characteristic formula. So here you sum over all extended column increasing diagrams, keep track of the number of inversions with the Q parameter, and then x to the phi is the monomial recording the number of times I appears as a label. And then basically this formula also stabilizes to a formula for R and lambda. So you take your, basically in order to get the formula for R and lambda, you take a limit as S goes off to infinity. This is the same thing as allowing infinitely many columns. And let me also note that there is another statistic which I call D-inv, or diagonal inversions, that gives you an LLT expansion. And it's more obvious why the D-inv statistic gives you a symmetric function. And I also want to mention there is a different formula for the graded Furbinius. So here's some standard notation for Q binomial coefficients, which we saw in Josh's talk. And I've defined this new statistic, n of mu lambda. And it turns out that the graded Frobenius characteristic has this nice expansion in terms of Hall-Littlewoods. So Q prime is the same thing as the Q reversal of H tilde. So you take your Q prime and you multiply by a product of Q binomial coefficients, and then you shift that by some Q factor. And then you take that entire sum and you Q reverse it. So if you've seen the formula for R and K, this looks very similar, except this product of binomial coefficients is one that doesn't collapse to a single multinomial coefficient. Okay, so those are our three rings. And let me address the star briefly. Is there a co-homology ring for the ring R and lambda? So this is work in progress with Levinson and Wu. We think we have found a compact singular variety whose cohomology ring is R and lambda S. But in this talk, I'll talk about a different geometric connection, which I referred to at the beginning of the talk in terms of coordinate rings. So this is in terms of the nilpotent diagonal matrices. So maybe a moment's thought reveals why nilpotent is in quotes, because what is the only nilpotent diagonal matrix? It's a zero matrix. So this is something, so we'll have to go to scheme land. So we'll denote O lambda to be the set of nilpotent matrices with Jordan type lambda. And you can define one of those matrices, you can define that set of matrices by some rank conditions. They're defined by the ranks of the powers of that matrix. And here, this P statistic is the same exact one that shows up in the definition of the Tanisaki ideal. And when you take its closure, the closure of the space, this equality turns into an inequality. And we'll let T be the diagonal matrices. And De Concini and Procesi were able to prove that not only is R lambda a cohomology ring, but it is also the coordinate ring of the scheme theoretic intersection of these two varieties. So this is the scheme theoretic intersection. Geometrically, for those algebraic geometries, this is a fat point. And how do you generalize this? Well, so Eisenbud and Saltman defined a generalization of those matrix orbit closures. They took a partition of K, just like in our setting, and defined this variety, O n lambda bar, to be the set of matrices that satisfy a certain rank condition. So here on the right-hand side, we're tacking on n minus k. So basically, you get matrices which are no longer nilpotent. And as an example of an element in this variety, you have block matrices, diagonal block matrices, where A is in O lambda bar, and B is any n minus k by n minus k matrix. And Wayman was able to find an explicit generating set for the vanishing ideal of this variety. And using that, I was able to prove as a corollary that R n lambda is isomorphic to the corresponding scheme theoretic intersection with the rank varieties. So all of the results on R and lambda transport over to this setting. And just to finish, further directions, I would love to know if there were a delta prime analog that was related to these graded Furbinius characteristics. And along those lines, is there some kind of Macdonald polynomial version of these graded Frobenius characteristics with a Q and a T parameter? And maybe that would involve generalizing the major index statistic. So thanks a lot. Thanks for your attention.
Thank you.
Let's stop the sharing so you can see everyone's on the screen. Great talk. So let's move to the questions in the room.
Right. The first one was asked by Andy Wilson. I'm going to ask Andy to unmute himself and ask. He's a co-host anyway.
Sure, yeah. So can you get a monomial basis from these statistics? This is probably in your paper and I just don't remember, but.
Oh, okay, so there is a monomial basis. Yes, so I think this is one of the things that Rhoades, Yu, and Zhao worked out, is that actually their motivation for coming up with the inversion statistic came from looking at the monomial basis that I proved. So yes.
Thank you.
Question from Maria. Maria, unmute yourself.
Yeah, it just occurred to me during your talk that there's this paper by Team Schilling that got this crystal structure on ordered set partitions and gave the interpretation of the Furbinius characteristic for RNK. I was just wondering if you looked into any kind of crystal structure on the lambda shifted ordered set partitions.
So what I know is that Minimag seemed to be, or from what I've heard of that project, Minimag seemed to be the best statistic to work with for the crystal structure, but I don't yet know what Mag or Minimag would be. Yeah, so that's a great question.
I see.
Maybe you could do it for like 2-column partitions, say.
Mm-hmm.
Next question is from Joshua. Feel free to unmute yourself and ask it yourself.
Oh, sure. I was just wondering if the generating function of the Rn lambda S's, like a trivariate generating function or something like that, was interesting. Mostly I was wondering if there's like a decomposition of some larger object. Like I have in mind the Thrall's decomposition of the universal enveloping algebra of a Freedly algebra.
Yeah, I don't know, but that's a great question.
Okay, fair enough.
I'd love to know if there was one though.
Yeah, sure.
And there's one more question by François Bergeron, and I'm going to ask him if possible to state it himself.
Yes. If you think of the Garsia Procesi module rather than a quotient, but as the orthogonal complement of the ideal, this is essentially the same for a nicely chosen scalar product, then you can polarize and get the Garcia Eman module, which have the Macdonald polynomial as bigraded Frobenius. So do you consider doing this the same for your construction?
I haven't worked that out yet, but so I should have mentioned one of the things that Rhoades, Yu, and Zhao do is to find these orthogonal complements for this case, for the one variable case. So yeah, that sounds really promising, trying to get a 2-parameter version, yeah.
Okay.
But I don't know what that would be yet.
Okay, so we're perfectly on time. Let me thank Sean again and give back the ball to Laura.
Great talk.